Hi, my name is Tobias Knopp from the Institute for Biomedical Imaging in Hamburg. In this talk, I will outline a new background correction method for magnetic particle imaging that uses a dictionary approach. Magnetic particle imaging, short MPI, is a tracer-based tomographic imaging modality that allows to determine the concentration of magnetic nanoparticles. It has a very high temporal resolution of up to 46 volumes per second, a high sensitivity in the picomole range, and a medium spatial resolution of about 1 to 2 mm. MPI can be used in a variety of applications, for instance for vascular or perfusion imaging. In practice, the high sensitivity is limited by background signals that disturb the measurements. Without proper handling of these signals, artifacts appear in the reconstructed images, like it is shown on the right. In this experiment, only a point sample is located in the center, but on the left-hand side one can see an artifact that increases over time due to a drifting background signal. Sources for background signals are, for instance, disturbing signals from the environment or thermal scanner drifts, both of which cannot be fully avoided. The imaging equation in MPI can be expressed as a linear system of equations. U equals S times C, where U is a measurement vector, C is a particle concentration vector, and S is the system matrix, which is usually measured using a data sample in MPI. The ideal voltage signal is in practice superimposed by two additional components: a static background signal and a dynamic background signal that may change over time. We consider a series of L images, and small l is the frame index. One way to determine the background signal is to measure U without particles in the field of view, as it is shown on the right picture. With this method, one can reliably determine the static part of the background signal. To deal with background signals, one can use one of the following methods. First of all, one can measure a background signal before an experiment and subtract it from all following measurement vectors. This method is simple and widely used in MPI. It cannot handle dynamic changes during the experiment though. In the past, we proposed an extension of this method where one uses two background scans, one before and one after the experiment. With this, it is possible to model linear background drifts. One issue of this method is that it substantially complicates the imaging protocol, since it is not always possible to remove the object immediately after the experiment. Straub and Schulz were the first to propose a joint estimation of background signal and particle concentration. They used two subsequent frames that were slightly shifted in space. Then, they used an optimization approach where the particle signal was assumed to be static over these two frames. While this work was very innovative, it has not been adapted by other researchers so far, since it requires an imaging protocol that is not being implemented in most MPI scanners. The objective of this work is to develop a background estimation approach that can be applied to any MPI sequence. There should be no need to measure background scans directly before or after the experiment. Our approach is outlined next. In the most general form, a joint estimation of B and C can be expressed as the optimization problem shown here. We have a data discrepancy term that includes the background B, and we have two regularization terms for C and B. For C, we will use an L2 prior, which is common in MPI. We note that the regularization term for B is mandatory, since without it, C equal to 0 and B equal to U would be a solution of the minimization problem. The core proposal of our work is to use an orthogonal background dictionary phi. Based on it, we can define the background space gamma to be a linear combination of all columns of phi. The proposed regularization term now puts a penalty to solutions that are far off in initial guess BS'd. And additionally, we put a hard constraint on B to be part of the background space. By substitution, we can pull the initial estimate from the regularization term, here, to the data discrepancy term. Then we replace B by phi n, which allows us to get rid of the indicator function. Note that from now on we optimize the coefficients n instead of the background b. Then we choose the regularization term acting on the coefficients n to be a weighted L2 prior with weights discussed later. On the next slide, we aim to bring this optimization problem, shown here, into standard Tychonow form. To this end, we define the matrices D and the vector y that allows us to stack the norms together. Then we vertically stack the matrices S and phi and introduce the vector w, which then allows us to express the problem as a times y minus w in the L2 norm plus d times y also in the L2 norm. And this is an ordinary least squares problem that can be efficiently solved. Next, we discuss how to determine the background dictionary phi and the weighting matrix W. To this end, we use a set of background measurements U1 until U theta that are commonly measured when calibrating the system matrix S in MPI. Thus, in practice, this data is already available for most MPI systems. Since the background signals are all very similar, and since the drifting part can be much smaller than the non-drifting part, we apply a singular value decomposition, and then use only the Q largest left singular values as the matrix phi. The matrix W is used to weight the matrix phi according to the magnitude of the associated singular values. In this plot, one can see the singular values of a typical background matrix. It can be seen that the singular values decay rapidly, such that the number of background coefficients Q can be set to a small value. On this slide, we summarize the proposed background estimation method for a series of L measurements. In line 1 to 4, the matrices are set up. Then the optimization problem is solved for each frame individually in line 7, after subtracting the initial background in line 6. In lines 8 until 10, the solution vector is splitted into the components associated with the particle concentration and the background signal. Our algorithm is evaluated on experimental data measured with our custom-built head scanner, shown on the right. It has a low selection field gradient of 0.2 Tesla per meter, a 6 millitesla excitation field strength, and samples a horizontal plane within the scanner, indicated in blue, along a Cartesian sampling trajectory. The field of view is about 140 times 140 millimeters squared, and the temporal resolution of the scanner is 2 Hz. In our first experiment, we started the measurement with an empty scanner. Then, we put a static dot sample into the center, where it remained for about 65 seconds. This allows us to analyze background drifts and the associated artifacts. One key challenge of our algorithm is the selection of the 3 parameters lambda, beta, and q. Here we propose an approach where first lambda is optimized without background estimation, and afterwards beta is optimized by visual inspection of the reconstructed images. Here one can now see the results for the parameter optimization. For large beta, shown in the first column, the background correction is basically disabled and does not remove the artifacts. With increasing beta, the artifacts are reduced more and more. However, simultaneously, one can also observe a loss in spatial resolution of the reconstructed dot sample. Thus, one needs to trade off background suppression and spatial resolution. Fortunately, the results are similar for q larger than 1, which implies that this parameter can simply be set to a high enough value and then kept static for a specific scanner. We also made a quantitative analysis where we can see that beta of about 10 to the minus 6 maximizes the SNR, while the full width at half max of the dot is only slightly increased. On this slide, all three background correction methods are compared. Left, the static background correction method, which shows strong artifacts. In the middle, the linear interpolated background correction method that performs much better, but also shows a small artifact, which is due to nonlinear signal drifts. Finally, on the right, the proposed dictionary-based background correction method that yields the best background suppression with only small loss in spatial resolution. Here we also made a quantitative analysis that shows that the concentration in the sample is much more stable over time. Also, the SNR of the signal is much higher for the joint background estimation method. We finally also performed experiments with a dynamic change in tracer concentration. Here we can see a brain phantom consisting of two brain halves that are perfused via two ingoing and two outgoing hoses. The results of this experiment are shown here. It can be seen that both brain halves are perfused and then leave the phantom. Here are the two brain halves. For the static background correction, one can see an artifact after the tracer has left the phantom. Here. These artifacts are successfully removed by both the linear interpolated background correction method and by our proposed dictionary-based approach shown on the right. In summary, we have proposed a new method for background correction in magnetic particle imaging. It has the big advantage that it can be applied to any MPI measurement sequence and does not increase the complexity of the imaging protocol. Parameter optimization is certainly a challenge for the practicability of our method. The code and data is openly available on GitHub, where we integrated the algorithm into our image reconstruction package, MPI-Reco. As an outlook, we want to investigate the generalizability of the dictionary across imaging parameters, such as the gradient strength of the selection field or the excitation field strength. Also, we would like to introduce a prior that constrains temporal fluctuations of the background signal. And with that, I want to thank you for your attention and acknowledge financial support of the DFG and the BMBF. Bye.